store semantics on top of the Ethernet anytime soon?
Sorry, which?
It's like so the memory read write the kind of semantics. It's just like a CXL, except the PCIe.
I'm going to go officially with no comment on that one.
Unofficially?
Unofficially on the recorded line that people are listening. Thanks, no. I'll pass.
Dan? Yeah.
Say anything about HP's plans to bring Ultra Ethernet to market? Is there going to be a slingshot NIC we can actually get outside of a Cray type system that implements all of this in the near future?
You know, I can't talk about product roadmap in here.
Some of it's public. You don't have to give me a date or a speed, but certainly not a price.
Blink twice as yes. Sorry, I'm not going to comment on the roadmap.
Any other questions? Non-product related questions. Anything remotely? I think Pankaj, yes, please unmute Pankaj and go ahead, Pankaj. Is he unmuted? Yeah.
Thanks. So very quick, what did we learn from putting RD and UD in InfiniBand? My understanding is it was there, but was not getting used and eventually sort of fell by the wayside. What is your lessons learned from putting RD and UD in InfiniBand?
Sure, I'll comment on that. So you need to go look at what the RD spec actually says. And it was not possible to build a particularly interesting implementation of RD because of the way it was written. And I forget the details, but it's something like you could only have one outstanding at a time or something like that, and nobody really wanted to do that. UD is used. UD has been used early. The very first slingshot systems that shipped had a Mellanox NIC in them with slingshot switches. There was only a few of those that shipped, but the very first slingshot systems were like that. And we actually built protocol over top of UD in those systems for scalability. And so UD actually does get used. It's just that to use UD, it throws some of the reliability up the stack, which is fine in a very highly reliable network. But it's not, even then it's not awesome. You'd like to get even that processing off the host.
Thanks for those comments. Yeah.
Okay. Any other questions from here or remote? I'm sure over coffee break or banquet or wine, you can talk about products. Okay. So let's give a big thanks to Kip. Okay. So we'll move to the next talk. It will be presented by Professor Martin Schulz. He's a full professor and chair of the Computer Architecture and Parallel Systems at TOM. Let me call. Is Matt here? Somebody can extend help to set him up. Yeah. So which he joined in 2017, as well as a member of the board of directors at the Leibniz Supercomputing Center. Prior to that, he held positions at the Center for Applied Scientific Computing at Lawrence Livermore National Lab and Cornell University. He earned his doctorate in computer science in 2001 from TOM, and then Master of Science in Computer Science from Illinois. And his research interests include parallel memory system optimization, all aspects. He has done a lot of work on all different things, but his latest work is on quantum computing, and especially quantum computing architectures and programming with a special focus on HPC and quantum computing integration. He has published over 250 peer-reviewed papers, and as many of you know, he has been serving, I think, how many years on the MPI Forum chair? I think under his leadership, I think MPI 4 was introduced and MPI 5, And I think already the discussion has started moving into the MPI 6. He was also a recipient of the IEEE HCM Gordon Bell Award in 2006, R&D 100 Award in 2011. He served on many conference and workshop organizing committees, including as a program chair for ISC 2021, PC area chair for IPDPS 2021, and general chair for Euro MPI 2021. And I remember, Martin, I think you came to OSU in one of the very earlier years, IPDPS 2006 or 2000, or even earlier than that, for a piece.
Yeah.
That's how I got exposed to him in person.
It's a very cold winter.
Yeah, it was a cold winter. That he remembers. Okay. So let's welcome Martin. Okay.
Yeah, thank you very much for the very kind introduction, for the invitation. I do remember that first visit, yes, because it was very cold, but it was also a very fun visit. So, so thank you for the invitation. I'm going to talk about something completely different. I promise some slides will have the words MPI on it, and it will be in context. But this is something quite different that we have been up to over the last couple of years. We're talking about working on quantum computing and how quantum computing fits into HPC and how we need to connect those together from the hardware side, but also from the software side. And just to give a little bit of context for those of you who are not familiar with quantum computing, I will not go into formulas. I will not talk about physics. I'm not a physicist. I'm a computer scientist, so there's a very high-level view. But why are we trying to do this quantum computing? Well, basically, we're trying to build a system that works on quantum mechanical principles. And so we're trying to use some of these new features that we see in quantum mechanical systems. For one, superposition, which means we can have a piece of information can have any state, can all states at one time. Until we measure it, then it falls back to a 0 or 1. And we can entangle multiple states. We can actually connect them, and so they behave together. And with that, we can open the state that we can simulate. Systems are also probabilistic, so it's nothing where we just run an algorithm, we get a final result, and that's it. We actually run experiments many, many times. They're really basically physics experiments. We get a distribution at the end, and then the result with the most likelihood that comes most often is basically the result that we accept as true. There's errors involved as well. It's really probabilistic, so we order of hundreds to thousands experiments that again aggregated to the final result. The basic unit is a qubit. So it's kind of the counterpart to the bit, with the idea it collapses to 0 or 1. When you read it, it's the idea of it can be superposed or entangled, right? And then when you read it, it gets down to a 0 or 1, and that kind of gives us the information. We can have multiple qubits. With that, we can get large state spaces, and with that, we can do basically store and can have the information that we want. And you program this whole thing with gates, and this was one of the most confusing things for me coming from the architecture community. They mean with gates something completely different. A gate is an operation that you apply to a state. This is nothing physical like we have it in the hardware part. Basically, it's a kind of transformation you can do. Is you do this with some kind of way of manipulating the qubits, depending on technology. This can be lasers, can be microwaves. But basically, you send a pulse down to somebody, manipulate that. With that, you can get into superposition states. You can get the entanglement done, and also you can measure these things at the end. So why are we going through all this trouble? Well, the hope is to get to something called quantum advantage, which means we want to get faster than we have in classical systems. And this is very selected. There is some algorithms that people have shown that there is a potential to really change the complexity of the algorithm. It's not just make it X times faster or change a constant, but you're really changing the complexity, get from exponentially to something that's under exponential, and that has the big advantage. But this is something that still has to be fully proven in practice. But in theory, that's the promise, and that's why people are working on this, including us on this topic. This has, of course, some hopeful application domains, but those are relatively limited. So this is not a universal principle that you can apply to anything. So don't expect that your PowerPoint will run on a quantum computer anytime soon. Quantum simulation, of course, is simulating quantum states with quantum computers is one thing. Optimization, machine learning is other application areas that people are looking at, and also quantum linear systems. So these are kind of the areas where we know some algorithms. Besides, there's a lot of algorithmic work still that has to be done. And that also comes along right away with the challenges. Right now, systems are relatively small. We have only a small number of qubits, typically in the dozens to hundreds. These systems are still very noisy, so they have errors, which makes the probabilistic approach even more important, even more tricky. They also can't run very long because errors accumulate. There's only very few algorithms, very specialized programming. They're still busy with physics experiments. And we really, when we started, we took the physics thing out of the lab and it looked like a physics experiment. They're starting to look more and more like what we would consider a computer. But this is a process, right? So this is really a maturing technology that we're trying to bring into the compute ecosystem. And also there's a need for the integrators into the HPC, and I'll get a little bit more into this in a second. But these are kind of the challenges we're trying to solve. And there's a large effort to make a little bit of advertisement for home. In Munich, the Munich Quantum Valley is an enlarged initiative funded by the state of Bavaria, plus a lot of funding from the EU and the federal state as well, to really develop this ecosystem for quantum computing in Bavaria. Multiple technologies, that's the point. This is very much different to some of the other approaches. We really looked at multiple technologies from the beginning, superconducting, ion trapping, neutral atoms, and also we looked at the quantum HPC integration from the very beginning. With the mission to really develop quantum computers, to develop the software ecosystem, and also to build these quantum computers and operate them as well. So the idea is to get them also in the industry hands and into application users' hands to really use them and show the benefit of this one. And already with that also, we want to really do this as a full stack. So there's really a sustainable ecosystem that works across the whole environment. As part of that, we work with multiple technologies. There's trapped ions, which are developed at the Max Planck Institute for Quantum Optics, which is located on campus as well. So they work with atoms that are manipulated with lasers. There's the superconducting one. That's the one you typically have in mind when you hear about a quantum computer. These big cryo fridges, they have superconducting chips in them. They're developed, in our case, by the Walter Meissner Institute, which is a physics institute for cryophysics. And then we have the software stack as well, which is developed at the university as well as the Leibniz Supercomputing Center with teams on both sides to put a stack. And that kind of then hopefully bridges the whole thing from the low-level hardware to the application users. This whole thing comes with startups as well. There's a startup out of Max Planck. There's a startup out of WMI, P Quantum. We're also working with IQM, which also comes out of the Munich ecosystem. Some of you may have heard of that company. And there's also a software company involved as well. So we're really trying to build not just a research effort, but also the industrialization effort around it. And it's a huge effort. There's about 400 people working on this in the Munich area. And you see some of the other key numbers. And of course, those numbers are growing. So it's kind of an exciting effort. And particularly exciting is, let's just talk about this in, oops, I think I lost my battery, I guess. I get back. So this is okay, let's try this. Okay, I can use this. This is fine. Yeah, thanks. Okay. Okay. So the other fun part is that this is not just theory anymore. We actually have some of these devices and we can actually use them and we can build the software for that. So they're no longer just physics experiments. We actually have them in the center. So those are two pictures out of the Leibniz Supercomputing Center, of the Quantum Integration Center. You see on this side, an ion trap system by a company called AQT, Alpine Quantum Computing, or Alpine Quantum Technologies to be precise. And then this is the standard one that you're probably more familiar with from the pictures. It's a superconducting, in this case, an IQM system. You have the cryostat here. So the chip sits actually down here in the bottom of the cryostat. Above is this beautiful golden chandelier that you always see in the pictures, which is actually completely not functional. It's just wires, nothing else. And then over here, you see the control electronics, which can actually guide and send these pulses, send this gate information over, right? And this is the kind of part then where we connect to and control this from the software side. So those are kind of early examples of quantum computers, but also, as we said early on, that's also why we have the title Integration Center up there. These things will not work alone, right? So quantum computers will not replace HPC. We'll not have to give up programming MPI because we still need that in that sense. But we kind of see quantum as quantum accelerators as part of the HPC ecosystem, where this is another accelerator technology that we need to continue driving HPC to the performance that we would like to see in it. So really see this very much as part of high-performance computing, and as we're treating as part of high-performance computing, let's also bring it into the compute center, not having it as a separate addition to that, which then also means you want to add the compute capabilities to the supercomputing portfolio and work as part of that. And then, of course, the first requires a strategy on how to bring these things together. So again, why are we doing this? Well, if you look at what a quantum system really is, I showed you the refrigerator, I showed you the control system, but these control systems are getting more and more complex. You need control every single qubit in the fridge. So once we have a 5, 6, that's simple. Once you get to dozens or hundreds of thousands, that's going to get really complex and be distributed systems by themselves. You need to do data staging and the data post-processing. That will also happen in classic systems. Where you set a very specific algorithm, very specific kernels. And so you need to be able to kind of combine this with the rest of the workload. So you have hybrid workloads. Some of them need a very tight interaction, which means back and forth between the quantum and the classic side. And then one thing that's sometimes underestimated is the compilation, the process of building the right programs for that, to compile it, to optimize that. That's itself a very complex job and needs HPC resources and needs a very high demanding runtime environment. And we're also trying to put this onto the HPC side. And with that, the goal is to use this as an accelerator for HPC workloads, very similar to what we're familiar with other accelerators, where you split out the kernels that are good to work on that accelerator, that have an algorithm that suits this very well, and then basically do an offload from that. Similar what we do with on-node accelerators or with larger disaggregators like a Cerebras system, for example. And by the way, even the on-node stuff isn't not so crazy as it sounds. There are actually companies who are building small quantum computers on PCI cards these days. So you could actually even potentially think about at some point having a PCI card with a quantum computer in every node. We'll see how well that works, but in its scale, but at least that idea is out there as well. And so as a consequence, what we really would like to see is to run the HPC and the Q system as a single system with a common software stack, that we have the right tools to kind of go across them, that we have the easy access also for the HPC community for programming these systems in an easy way, in a way that we're familiar with it, to integrate a single programming environment, also to have the access experience kind of unified. So basically we launched this as an HPC job that then offloads. And this requires, of course, to bring this whole thing together and really have this close integration, both in the software, but also in the hardware side. And to start with the hardware part, so we want to bring the control system into the environment. And so this is how quantum computing typically looks like these days in most cases still. So you have an HPC system, you have a front end to that, you have a quantum system with its own control network with its front end, and there's some kind of long wire connection in between. If you're lucky, you're in the same building or in the same facility. This could also go over the internet with separate queuing, with separate queue management, user management, and so on. So that's typically kind of this loose coupling, which works for some application, but once you start getting tightly integrated, it's going to get tougher. And so what we actually started doing is the following. We actually wanted to cut out that backbone facility, connect it directly into the high-speed network. We're dealing, in this case, either with a fast Ethernet part or even connected with InfiniBand into what we call the quantum access node, which then has a control network. So that already eliminates the first gap. And the final thing where we want to shoot for is actually bring it really to the point that every node can access the control system directly. That of course requires some software, some resource management and so on, but then you really have the access from every node into the system, and the software stack also runs on the HPC system. So future systems that we're currently building up will look like the one on the right side, with this really tight integration into a single environment, into a single system image. And that, of course, means bringing this together onto the same floor. So this is a mock-up model that we started early on, where we said, this is a quantum computer here. This is our rest of our machine floor. And this would be a future system at some point. Well, today it looks like this. So we managed this part. On the left side, you see QXA, which is the first German demonstrator. It's a 20-qubit IQM system. And you see it's on a regular machine floor and back with our regular compute systems. What looks trivial here was not quite as trivial, because you're dealing with gas handling systems, you're dealing with different water quality, you're dealing with compressors, you're dealing with vibration on the floor, we're dealing with electromagnetic wave, noise, all this stuff a quantum computer doesn't like. And so we had to do extra shielding at the experiments and stuff like that. But we can now actually run this, and this actually runs very successfully in the same environment. And this now, we're currently building up the second system right behind it. That's actually almost done at this point. Unfortunately, I don't have a picture of that yet, but it will be available in the next couple of months. So that was installed, as I said, in 2024, so last year. We started with an early user phase, and we're currently transitioning into standard operations. So this is a really becoming a tool for our scientists to work with. And this is from the inauguration time. The quantum team that built this up back then, this is what they called themselves the excited state. This was after the first complete run of a quantum accelerated HPC chip, to our knowledge, the first one that would ever run for a system that was done on premise together with the HPC system on the same floor. And looking forward, we're currently in the process of installing the next one. So the 54 qubit is coming, it's being installed right now, and it will be 150 qubit in 2026. So we're kind of building up that line. This is part of the European efforts to build HPC QC systems. So I've talked a lot about hardware now. Of course, now the question comes, so what about the software, right? So far, these things have been lab experiments. So a lot of the software has been ad hoc, Python scripting, experimenting with individual states. People have been interactively playing with individual pulses. There's, of course, no way to run in an HPC center. So what we want to really get to is a really integrated software stack, which then also integrates with the HPC side. So what we're going to get from domain experts on one side, so not just physicists, but really domain experts, to a series of quantum devices so that we can basically choose which one we use. It's really not clear which one is better, which technology fits. Actually, the best guess is that certain problems will fit better to other technologies. And so it will have to be, you pick the right technology based on your problem if you have multiple available to that. And currently, the software stacks look like this. So it's kind of individual users for individual devices use their own stacks. And what we want to get to is something like this, where you have finally into an intermediate representation that is hopefully standardized. So working with the QRI Alliance, which is an alliance of like 7, 8 major players in the field to build up a standardized intermediate representation based on LLVM and MLIR technologies. And then from there, go to the quantum devices. So we can connect to different hardware from different user groups, and of course also have the connection into the HPC part so we can have this acceleration part going. And as for requirements, we want to support a wide range of modality. That was always high on our list to kind of make this work across the different technologies, superconducting, ion trapping, neutral atoms, support a wide range of programming models, do this integration part, as already mentioned a couple of times, to really have this hybrid programming so we can build on and work with traditional HPC programs, like particularly MPI plus X programs. Resource utilization is a key part. HPC is expensive, quantum is expensive, and so you want to make sure there's little idle times. You just don't want to offload and have the HPC system wait for hours until the quantum system gets to the job and comes back to that, so that requires a little bit more clever scheduling parts. System management is also something where we want to get the administrators on both worlds together to understand the different worlds and make sure they can deal with the system as a whole. And the software stack is also not just intended for us, but is really also intended for external installations in different configurations. And so the system looks actually, at the end, very similar to a classic system, but with a couple twists to that. So you start with a program, you run through a couple of compilation passes. We start with some device agnostic passes, so we don't know yet what kind of technology we're shooting for. Then we do a device selection. We select which device you want to shoot for. After that, you do some device-specific compilation processes, again with passes going through that. And then at the end, you have a thing that you can submit. You need to query in between which device is available and what the status is, which already means this is not a static process, this is a dynamic process. So everything happens at runtime here, which is a big difference to what we typically know in HPC. We also want to take device constraints into account. So what's the native gate set, what's the technology, and also how well are you doing? So which qubit is good and bad at the moment? This actually changes on a regular basis between calibrations, so we need to take that into account. I have an example of that afterwards, and then how we do the proper job submission and how we get to calibration data in, right? So this adds a couple of very specific elements too for the quantum side, but we're reusing a traditional compilation flow in between. And for these kind of especially things particular to us, the hardware side, we started developing an interface called the QDMI, the Quantum Device Management Interface, that allows us to do exactly that, to send jobs to the devices, to get the results back, but also get these characteristics back that we can feed back into the compilation process, adjust what we're compiling and optimize for a particular device. We started calling those FOMACs, figures of merit and constraints, that tell us how good a device is doing, figure of merit, and what it can and cannot do. This is the constraints, and with that we can feed the compilation process. This is a pluggable system, so we have a whole bunch of backends that you can plug in. So we can separate vendor-specific technology from the open stack on the left side. And with that, have the ability to actually decouple the vendor part from the rest of the stack. So when we find future procurements, we're going to acquire implementations to this QDMI, and with that can plug them in right into our backbone. QDMI is an open interface. This is also published open source. If you're interested in that, feel free to take a look at that. The URL is on the bottom. We're also welcome to contributions, of course. It's a C API. If you look at that, you know MPI, you will actually see some similarities there. Some of the semantics and some of the structure is very much inspired by MPI. It's intended as a connect again to the vendor side on one side and then to the software stack on the other side. It has this plugin concept for the backend, so you can customize it to different backends. We're working with many vendors, and all our systems that we have in our lab and we work in the Quantum Valley with already have the backend. So this is kind of a growing number of backends that we support. And then there's a flexibility also to read these properties. So we don't want to prescribe too much. So there's a key value-like abstraction, so you can ask for properties out of the system, and you can feed that into the compilers. And there's also multiple levels of abstraction that are supported in that. And then this whole thing is not just an academic software, and I get to this towards the end a little bit. The stack is actually really intended to be as a production stack that we use ourselves for our production system, that our startup companies can use. So there's all the software engineering is put on top of that. And anybody who I'm talking to here who knows how to do production software knows that this is not an easy feat, and it actually takes a lot of effort to get right. And so we're putting some extra effort into this part as well. And with that, we can start building up the rest of the stack. So we have the interface to the backend. We have interfaces for system administration and telemetry. We're actually having a whole bunch of sensors in the lab. We have about 1,000 sensors to understand the environment these quantum systems are working in and what does it mean for the results. Anybody's interested in that, I'm happy to show some of this information offline. I have some of the slides for that, just not enough time today. We also grabbing these figures of merits, as I mentioned already, from the system. And with that, we have the information now that feeds into the compiler. And this was actually one of the first ones actually where we also started to combine the software stacks from the HPC side and the quantum side. We've been developing on the HPC side a library called SysSage, which is basically a topology management library that allows us to understand the topology of classic systems, where the CPUs, where the GPUs, where the memories, basically an HW log on steroids with additional dynamic information. And we can track this then there, and we can kind of use this for optimizing HPC jobs. Some of the same information, though, is useful now on the quantum side as well. So where are these qubits, the static properties? How can we track their quality? What is the connectivity on the chip? Also, that's topology information. Quality is like dynamic properties, is similar like to bandwidth and congestion properties. So we started using this library also on the quantum side and really map these things together into shared data structures. So you can now have a shared view of your combined HPC-QC system and also start optimizing across both. And we can do things like this. This is the number of a certain number of qubits on the QX system over time. You can track the quality levels. You can clock the topology information without now starting mapping a problem which has a topology by itself in the right way onto the hardware so that we get optimal execution at the. So if you're interested in that, there was a paper on this at ISC, actually won the best paper award that actually explains this. So if you're interested in that, I want to point you to this particular paper. This we can now use to kind of build a compilation framework, to build these compiler passes in between. And this SysSage is not just one component that we have multiple components. There's been a large effort in the MQV, so there have been several components now that have different programming models on the left, compiler optimizations, backend optimizations, also system interfaces that we can now pull as components into the software stack and build up the overall software stack. There's a connection into the resource management now. I already mentioned we need to make sure that we have the right system available at the right time. So this is a scheduling problem there as well. So we need to work on the scheduling side to make sure we have the right systems available. And once we do that, the next question, of course, how we do program. And I want to spend the last couple of minutes of my talk to talk a little bit about some of the ideas we have on the programming side. If you now look at an HPC job and how would you access a quantum system through the HPC job, well, if you look at a standard HPC job, you have a gateway, you log in, you start some of your germ, you get a Slurm, the Slurm would start up your compute node, you have your parallel application, you have some acceleration with something like CUDA, of course you have MPI to connect the various jobs together. And so we thought it was a natural thing just to add a quantum programming interface to that as well. Similar idea as with CUDA, that you can accelerate from the HPC job directly out. Of course, you don't have a quantum system on every node, unless you have one of those PCI cards that I mentioned before, but it's not that common these days. So what we actually did is we connect this to the quantum daemon, which then does the compilation, the runtime facilities for that would go to a backend architecture, would then kick off basically the device selection, and then go straight to the system, and with that close the loop. And so we can now run with a C interface directly out of an HPC application, and a similar idea as with an offload like with CUDA directly onto the quantum interface. Here's an example of how this could look like. So you can see here, we can define circuits on the quantum side. You can have then the circuits defined. The programming is still very low level, right? We have not been able to solve how you get away from programming in gates. This is something that nobody has solved yet. And unless you go very, very high level, then you just have a library. So we're still dealing with the gate abstraction, but you basically create this kind of widget here that is a quantum circuit. This is actually borrowed from OpenGL. Then you execute it. You can wait for the thing to execute, and then you get your data out. And you can process it afterwards, right? So it's a very simple idea of defining a circuit, sending it off, and getting it back. And if you're familiar with HPC program, which I think most of you are, you may say, well, this looks very much similar like a typical offload model like we have in OpenMP. And so we said, well, this is true, so let's try this with OpenMP as well. So we actually did as a kind of a proof of principle implementation. Quantum integration is part of OpenMP, so we extended the target idea into using the quantum computer as a target. You still have the gate abstraction part of here. The loop in here is now not a parallel loop, but it's just this multiple shot loop, the idea of doing this probabilistic experiment. But this whole connecting to the stack, doing the resource management is now hidden behind this pragma. So this was work done together with a few folks from the OpenMP community and between Tom and our compute center. So this is an experimental thing right now, would have to need some extensions on OpenMP to make it really stable and fully integrated, but at least we should be able to show that this works. And with that, we now have the complete left side. We have now the programming models as well. And with that, the stack now is connecting users on the left side through the programming models, through users management, compilation, the back end, all the way to the quantum system. And we have this full stack across modality approach. This is the final architecture of the MQSS, the Munich Quantum Software Stack, which of course we're still expanding. Everything in there will be open source. Some parts are ready, and we're kind of pushing this forward. And if there's interest in collaborating and kind of seeing how we can coordinate on interfaces and so on, please come talk to me. We're definitely open for that. So looking forward, where are we going next with that? As already mentioned, this is not an academic exercise only. We want to have this out in production. So we have a stabilization effort in place with I won't say commercial, but at least a non-academic effort to put this out as a production stack. We were evolving MQSS in the NISC areas and the noisy area with new backends with better optimizations. And the next big step that we're doing in the next version of the MQV is to do fault tolerance and error mitigation. So bring in this aspect into that, which have again impact on how the stack will be designed. But I think we can do a lot of the interfaces we can maintain. Then before I close, of course, this is not just my work. There's a large team behind it. This is the core team of the MQSS, together with Robert Wille, Laura Schulz, and also Lucas Burkholzer and Jorge Echeverria, who are our technical leads. And these are a big thank you to our groups or respective groups at the university and the Compute Center, which have made all this possible. And with that, I'm happy to take questions. Thank you.
This was a great talk. So let's, we have some questions. Go ahead. Yeah.
I just have a basic question. So you were saying until now, no one has been able to provide, I guess, an easy to use abstraction, and it's very programming with the gates and working with the gates right now. Can you tell us what, I guess, the main challenges or what's making it impossible right now?
Well, so just because there's the low-level access, which I think is very hard to approach. And then there's high-level approach, of course, an optimization library. Give me a problem and I will optimize it, but that is such a high abstraction that there's a big gap in between, right? The programming way is just fundamentally different. It's not a kind of iterative programming that we know of, right? You have to work on the quantum states. You have to understand quantum physics, basically, at this point. And there's like a whole branch of theoreticians that just work on quantum algorithms and try to find these. And there's only a few been found so far. So that's why you really have to be a quantum physicist at this point. And that's the abstraction at some point we need to crack.
So is the end goal to have some sort of mapping between like a qubit state to what that means for when we're trying to program something, or is it something like way beyond that?
Okay, that's speculation. Now, I would say you probably need something probably higher level that's not quite quantum physics, but I don't think it would look like anything what we know now as programming. It's a different way of thinking also behind it, and I think you cannot mold it in one into the other. I think then you would lose something. But how does it look like? I don't know.
We have a question from remote. You can read it here. It says, awesome. I heard that you employ both superconducting and trapped ion qubits approaches. Could you elaborate on the rationale for utilizing both methods?
Yeah, so in the quantum valley, we beginning said we want multimodalities because they all have their pros and cons. And it's unclear at this point which one will win, which one can we scale, which one can we stabilize to the point that we can do error correction more easily. And also they have different properties. So one is much faster, but shorter lived. The other one has longer times.